My apologies for being somewhat slow getting the key written for Special Quiz 2. When I wrote Special Quiz 2, I didn't recognize how much fun it was. So it took me a while to write the key, which I finally finished yesterday about 6 p.m. So that'll be up today. As I have already stated, I have in mind the content of Special Quiz 3, but I haven't written it up yet. If it doesn't get up today, it'll be up by tomorrow at the latest. You'll find it in the usual location on Sakai. And I made a goof on the key for Exam 3, so Exam 3 answer sheets will be rescanned. You may recall a series of reactions involving the formation of sodium chloride, where I forgot how to pay attention to the exothermic nature of a reaction and keyed the wrong answer. One of you was good enough to send me a statement about this. Most people got it right. When I glanced at the original scan results, I said, why did most people get this wrong? It was me who got it wrong, not most people. So most people's scores will go up. That'll be rescanned and reposted today. And I reminded you on Friday about the necessity on your part to view these videos which underlie the onset of Chapter 23, so that you have an understanding of why periodic size trends for A family atoms are as they are, getting progressively smaller as you go left to right across a period, and progressively larger as you go bottom to top. Top to bottom, down a family, A family atoms. But at the tail end of our last gathering, in regard to concluding Chapter 22 conversation, we came upon the issue of how to determine E0 for a new half reaction. The standard process for doing this is discussed in the notes, and we looked at this last time. The required recognition is that when you combine two or more half reactions to get a new half reaction, you cannot simply add the E0 values to get the E0 value for the new net half reaction. Because you have to have, to couple half reactions and get an E0 value directly, you have to have cancellation of electrons. Well, that process doesn't lead to cancellation of electrons. So you have to go through the changes of standard free energies for those half reactions. Not difficult, takes a little bit of arithmetic. But the best way to do this, if the data are available, is to follow the same procedure we use to determine Ka values for strong acids, the likes of which we did at the end of Chapter 21, using data from Table 1 at the end of Chapter 20, thermodynamic properties of common substances, with the data being reported at 25 centigrade, the data you see in Table 1. So a question in the notes on this is, how could we get E0 for this? Well, you go to Table 1 and you look up delta G sub F super 0 for the components of this half reaction system if the data is there, which it is for all the components of this system. 0, values there times 2, and the value is there for this stuff. So by application of Hess's law, you get delta G0 for this half reaction, That's equal to minus NFE0. N is 2. F is the Faraday, 96,500 coulombs. Calculate E0. You can do the arithmetic. In calculating E0 for this half reaction, go back to table 1. In table 1, you'll see that we have a half reaction contained in the table which shows the oxidation of calcium in the presence of hydroxide ion to make calcium hydroxide. But we don't have this half reaction in the table, nor do we have calcium being oxidized in the presence of carbonate ion to make calcium carbonate. But now you'll see that if we wanted to, we could put those half reactions in the table. But I thought the table was sufficiently comprehensive. You're looking at table 1 and the half reaction for the oxidation of calcium in the presence of hydroxide ion to make calcium hydroxide. What's the E0 value for that half reaction? Look at it. Tell me. What is it? Plus 3.2?
Plus 3.02.
3.02 volts. Okay? I believe it's the second strongest reducing system in the table. Is that correct?
Yes.
Lithium going to lithium-ion aqueous is the strongest for the table that we have. So if we calculate E0 for this half reaction, how do you think it'll compare to 3.02 volts? How will it compare? I have a vote for lower. Do we have any votes for equal to? I would hope not, because this material is clearly different from calcium hydroxide. How many vote for higher? And how many would just as soon not vote? We've been through the material which underlies the question that I just asked. What material do I refer to? What is the material to which I refer? In fact, you've done this in lab. KSPs. How does the water solubility of calcium sulfate compare to that of calcium hydroxide?
It's less soluble.
This is less soluble stuff, isn't it? That means this has a greater stability than calcium hydroxide in the presence of water, doesn't it? Is this occurring in the presence of water? You betcha. Well, then, if calcium sulfate dihydrate is more stable in the presence of water than calcium hydroxide, how is E0 for this going to compare to 3.02 volts? Got to be bigger, doesn't it? Hey, that's the kind of stuff you want to do always, the chemistry. That's what matters. Chemistry classes which invite you to do calculations all over the place without having you recognize what the calculations are based on, what they mean, that's a waste of time. Absolute waste of time. And unfortunately, I know 2045, it's presently conducted, is rife with that stuff. No good. No good at all. Because that doesn't get you to appreciate chemistry. If we did the calcium in the presence of carbonate ion, half reaction determination, how would E0 for that compare to E0 for this? Calcium in the presence of carbonate ion becoming calcium carbonate. How would E0 for that half reaction compare to E0 for this half reaction? Be still greater, wouldn't it? Isn't calcium carbonate even less soluble than this stuff in water? Hey, you've got the information which allows you to answer these questions, if you think about it. Now, I know the hard part at this stage of the game is for you to realize, what's the information that I should think about? But what have we been doing all along regarding extensive acid-base reactions, solubilities of salts, tendency to form a complex ion? In all cases, we're talking about thermodynamic stability, aren't we? All cases. All cases, then, for a reaction involving the formation of any such material, we're looking at the K value all the time. So keep in mind, anytime a question of this nature is being asked, stability, what we're asking you to think about. All right, you know how to do this then. One more fun question, which I believe I mentioned at the end of Friday's chat. If you look in our table, since the data are tabulated for 25 centigrade, and water solid by itself does not exist at 25 centigrade, and you had delta G0F for this, but you didn't have delta G0 sub F for this. Now this is in our table. But there are various and sundry hydrates for which you might want to get delta G sub F super 0. And you won't find that information in a thermodynamic data table. How might you approximate a reasonable value for the hydrate? Well, what you got to do is, well, go ahead.
Checking heat capacity or latent heat, and enthalpy, and doing entropy calculations.
Well, what we're going to do, or what I'm suggesting that you do, is to take data, the likes of which we have in our table 1, and use it to determine an approximate value for delta H sub F super 0 for water solid, and S0 water solid, from which you can get delta G sub F super 0 for water solid. Now notice in our table, take a look at the table. All these data points are present for this stuff and for this stuff. In the table, table 1, you see tabulated delta G sub F super 0 for this, as well as delta H sub F super 0, as well as S0. Same for this. Do you see that in all such cases, as I should think you would expect, delta G sub F super 0 magnitude-wise for this is bigger than for that. Delta H sub F super 0 magnitude-wise is bigger for this than it is for that. And S0 is bigger for this than it is for that. You see that? Are you looking at the table? Table 1, end of chapter 20 in the notes. In the calcium column. So at least to a first approximation, if I take the tabulated data point for delta G sub F super 0 for this stuff and subtract, and delta G sub F super 0 for this stuff, and take the difference, what will the difference correspond to? 2 moles of water solid, aren't they? Because that's the difference between these two materials. This contains 2 moles of water solid at 25 centigrade. Remember, chemistry just does all kinds of wonderful things. Free water by itself cannot be solid at 25 centigrade. But you put it in this compound, it's solid. Hey, this again is the principal component of wallboard. And I don't think at home you've seen your walls crying lately. You don't see them weeping. You don't see water dripping down from the plasterboard from which your walls have been fabricated. Maybe you think it's because the paint's on there. Keeps the walls from crying. We'll go home, get some sandpaper, rub off the paint, expose the bare plasterboard, sheetrock. You won't see the walls cry. I guarantee we wouldn't make walls out of materials which cry. Who in the hell wants to be in a house where weeping is going on all the time? Now then, if you also look at the delta H sub F super 0 data points and take the difference, you'll get a handle on twice delta H sub F super 0 for water solid. So if you divide that by 2, you'll get a handle on delta H sub F super 0 for water solid. How do you expect that to compare to delta H sub F super 0 for water liquid? You're in the table. Look in the oxygen column. You see delta H sub F super 0 for water liquid? Is it minus 285.8? How about that? Out of this table I see in my noggin too. So when we do the indicated arithmetic to get a handle on delta H sub F super 0 for water solid, before you do the calculation, what kind of value do you expect to get, magnitude-wise? Bigger or smaller than 285.8? Why? Are the bonds stronger in water solid than they are in water liquid? If you don't believe that, go try a belly flop dive into a frozen pond. Or jump out of a helicopter and land your head on an iceberg. See which gives way. Your noggin or the iceberg. But please let me know before you try this experiment, because I want to contact my attorneys about some very interesting students who decided to follow this interesting experiment, which I described in class, diving out of a helicopter into an iceberg. For some strange reason, the iceberg is still there, but the person isn't. They're lying in pieces around the iceberg. But they now know that bonds in water solid of water molecules to each other are stronger than bonds in water liquid of water molecules to each other. They will never forget. Now then, you also see S0 for this stuff and S0 for this stuff. Same question. How do you expect S0 for water liquid and S0 to for water solid to compare? Lower for which? Solid. Of course, and you'll get that. So I think this approximation is reasonable. Now then, if you take the difference of the delta G sub F super 0 values to get a handle on delta G sub F super 0 for water solid, what kind of number you think you're going to get before you do this approximation? Now take a look at, since you're in the table, take a look at delta G sub F super 0 for water liquid. It's minus 237.1, is it not? How about that? I saw that one too. Minus 237.1. Magnitude-wise, what kind of value you think you're going to get for delta G sub F super 0 for water solid? Magnitude-wise. A little bit bigger number. Now, do you think it'll be a lot bigger number?
No.
Why not?
The difference between the liquid and gas.
Well, first of all, you know the bonds are stronger in water solid, but you also know it has a lower entropy. These factors are working against each other. One tends to make magnitude of delta G sub F super 0 become larger. The other factor operates so as to make magnitude of delta G sub F super 0 become smaller, given that delta G sub F super 0 is certainly minus, because hydrogen reacts with oxygen quite vigorously, quite spontaneously to make water. Furthermore, how will delta G sub F super 0 for water solid and delta G sub F super 0 for water liquid compare at 273 K? At 273 K, delta G sub F super 0 for water solid versus delta G sub F super 0 for water liquid. At 273 K. They will be? Zero. They will be? Equal. Won't they? Is it water solid and water liquid? Aren't these materials in equilibrium with each other at 273 K? How about that? And 298 K is not that far above 273 K. So you shouldn't be surprised to find your approximation of delta G sub F super zero for water solid, given that it's for 25 centigrade, 298K, is going to be somewhat larger, but not a whole lot larger magnitude-wise, than minus 273.1. I get minus 273.3 for the water solid. How about that? I'm just showing you one more. You can get all kinds of stuff out of this thermodynamic properties information if you know how to monkey with it. And I'm trying to show you how to monkey with it. And a couple of the questions on Special Quiz 3 will involve monkeying with data. How about that? If I have my way, and damn it, I will. When you go away from this gathering, you're going to know one hell of a bunch of chemistry. That's what I want. I want you to be able to go to coming courses and just do a wonderful job saying, I got the foundation to get on with this stuff. Yeah, it's for you. And so we proceed to chapter 23, for which I issued a directive. Those of you who were here on Friday know about the directive. I'm not going to ask for a show of hands to find out who did or did not follow the directive. But I will tell you, for those of you who did not follow the directive, I'd already put you behind the 8 ball for chapter 23. So if you didn't follow the directive, follow it ASAP, as soon as possible. Because the first and foremost fundamental consideration that we need to be on top of when we go about the business of assessing strengths of Bronsted-Lowry acids and bases is that of the size of an atom in the bound state. Which means we need to be able to get a handle on the covalent radius of component atoms of molecules. Covalent radius rather than atomic radius. Textbooks are often very fuzzy in distinguishing between these two different properties of an atom. How do you expect the size of an atom in the bound state to compare to its size in the free state or unbound state? You expect it to be larger in the bound state or smaller in the bound state? Smaller. Why? Do you think the world in which we live abounds in bonds? Pretty damn strong bonds in there. I just hurt my foot. What do you think will drive in the main for bond formation to take place? Do valence electrons, when bonding takes place, and clearly the world in which you live abounds in bonds, you think valence electrons get more stable as a consequence of bonding or less stable? Why in the hell would you ever make bonds if valence electrons got less stable? That makes no sense at all. Back to this stability issue. The main thermodynamic consideration which underlies bond formation is the materials that you wind up with are more stable than the materials with which you began. And the only way electrons can get more stable is to get closer to or farther from the nucleus. Closer to. You're damn right. Because they're little protons and plus charge thingies in the nucleus. That's what stabilizes electrons and nothing else. So on a time average basis, when bonds form, valence electrons get closer to nuclei and become, therefore, more stable. Now then, some other considerations we'll have to be on top of are electron configurations. So let's take a look at a couple of questions on page 23.7 in chapter 23. Forget the first question. It's a good question, but I don't know why I put it there. It shouldn't be there. It's out of place. I mean, ionic compounds are brittle because it's an array of positive ions and negative ions. But if you try to bend an ionic crystal lattice, in so doing you'll force positive ions to get close to each other, or closer than they are in the lattice, and negative ions to get closer to each other. What happens when you get positive ions next to each other? Explosion takes place. In this case, crystal fracture. That's why these ionic compounds are brittle. So, next question. Chromium copper. How can I rationalize the ground state configurations of these two? I pick on these two. Whoop, 24 chromium. And 29 copper. Because when you learned how to write electron configurations, and in so doing learned about the Aufbau building order. Aufbau is a German word for building. Because a lot of this stuff that we do was developed by German scientists, physicists, over 100 years ago. These are the first two atoms in the periodic system which have ground state electron configurations that cannot be developed by simply following Aufbau. So let's jump up to vanadium number 23. Argon core, that takes care of 18 electrons right off the bat by writing this. You did this in 2045. By writing this, you are at the same time writing 1s2, 2s2, 2p6, 3s2, 3p6. Well, I can write this a hell of a lot faster than all that stuff. Followed by 5 more electrons. And if we retreat to scandium, we come to the first atom in the periodic system which has in its valence configuration what? A d electron. So it's the first transition metal atom. Argon core, developed in accord with Aufbau for scandium 21. Argon core, 4s2, 3d1. But independent of adding electrons to the 4s sublevel before we put any electrons at all in 3D, as shown by developing the ground state configurations for potassium and calcium, respectively, the first two atoms of period number 4. Because potassium is 4s1 and calcium is 4s2, but they have no 3D electrons. So energy level number 3 is not complete. But as soon as we put as few as 1 electron in energy level in 3D sublevel, pardon me, then, as if by magic, the 3D sublevel becomes a more stable sublevel than 4s. How do we verify this? We take an atom of scandium and subject it to ionization energy. We shoot an ionization energy cannon at scandium with the intention of removing the most loosely bound electron, and in so doing creating scandium single plus. What is the ground state configuration for scandium single plus? It's argon core, 3d1, 4s1. Now, if we removed preferentially the 3d electron and generated argon 4s2, scandium single plus would or would not be paramagnetic? Would or would not be? Would not be. Would be diamagnetic. But instead we generate argon 3D1 4S1. So by measuring paramagnetic character, after we perform this experiment in an ionization chamber, we confirm the fact that it's one of the 4s electrons that goes away first by observing that scandium single plus is doubly paramagnetic. That's how we find this stuff out. 3D1 4S1. Because one of the things you learned in 2045 was the so-called principle of maximum multiplicity. Remember that funny statement? What maximum multiplicity really mean?
That electrons fill empty orbitals, suborbitals before they double up.
If you have a collection of equal energy orbitals, like all the 3p orbitals in a p sublevel, or the 5 orbitals in a d sublevel, or the 7 orbitals in an f sublevel, okay? You will always singly populate all those orbitals before you make any electron pairs with no other factors being considered. Now there are some exceptions to that. The exceptions are shown by transition metal atoms in their chemistry. We may or may not get to that. But without those factors being considered, you singly populate orbitals, if they're of equal energy, before you make any electron pairs. Because when you make an electron pair, you have to pay an extra energy expense. It's called pairing energy. You hear about that in 2045? The energy requirement that must be met to get 2 electrons to live in the same orbital. Because when they're in the same orbital, they're as close to each other as they can be, which means their repulsion will be maximum. Because they're as close as they can be. Well, you've got to pay energy to make that happen. And that leads to the principle of maximum multiplicity. Now there's one other aspect of this principle, and that is when we singly populate orbitals, all the electrons spin in the same direction. Now this electron spin is really an interesting property of electrons. It has to do with precession about an axis rather than just spinning around like the Earth. But for a simple way to refer to electron spin, we'll say it either spins up or spins down. Spinning up electron is shown with a half-headed arrow pointing up. Spinning down electron is shown with a half-headed arrow pointing down. And when you got 2 electrons in the same orbital, they have opposite spins. How do we find this out? You measure the electron character of any atom or ion that has filled orbitals, and you find strictly diamagnetic character. But when you observe a species and have a configuration where you have 1 or more half-filled orbitals, practically speaking, the species with 2 half-filled orbitals is twice as paramagnetic as the species with 1 half-filled orbital. The species with 3 half-filled orbitals is 3 times as paramagnetic as the species with 1 half-filled orbital. That's how we find out these things are all spinning in the same direction. Because if they were spinning in the opposite directions, their spins would cancel and give us diamagnetic character. All right? So I write the configuration for scandium after I developed it like this. Rather than 4s2 3d1, which is the order in which I developed the configuration, but I write it like this after the configuration has been developed, because when I ionize this thing, the highest n value electrons always go first in the ionization process. It's a simple thing to obey because there's no exceptions to it. When you ionize any species, the highest n value electrons always go away first. All right, back to chromium and vanadium. Argon, vanadium. How many valence electrons total? 5. This is where the chemistry of these transition metals starts to get very interesting, because they have abundance of valence electrons, at least many of the transition metal atoms. And that has a lot to do with their chemistry, because they can develop a bunch of different oxidation states depending upon the chemical environment in which they are placed. So this thing is so V single plus is 3D3 4S1. And that's more paramagnetic than the V atom by itself. Because 3d34s1 has got 4 half-filled orbitals. This has got 3. And when you make vanadium double plus, then you go back to 3 half-filled orbitals. And the paramagnetic character becomes about the same as this. So, since this is developed by Aufbau, we would expect that this is argon 3d4 4s2. But chromium is not that. It is instead argon 3d what? 5 4s1. Explanation. A large capacity sublevel, particularly D or F. Because D is a 10 electron capacity sublevel and F is a 14 electron capacity sublevel. Because a D sublevel by itself is a composite of 5 orbitals, and an F sublevel is a composite of 7 orbitals. You can put 2 electrons in any orbital. It's all 2045 stuff. All right? The argument goes along the lines of a large capacity sublevel like D or F, when it's half filled or completely filled, is particularly stable. Because of what the theoretical folks call quantum mechanical exchange energy. I asked my quantum mechanically inclined faculty to provide me a working man's explanation of quantum mechanical exchange energy. They started with calculations, and I said, forget it. Because I don't know what this stuff means. So I just use this as a device for my 2045 students. I say, when you recognize that by not following Aufbau, you can instead develop a half-filled or completely filled large capacity sublevel, that's probably what happens. And we'll use that to account for the ground state configuration of chromium being 3d5 4s1 rather than 3d4 4s2. Same for copper. Copper based on Aufbau would be 3d9 4s2. But it is really 3d10 4s1, where we now have got the completely filled large capacity sublevel. So what are we going to do now if I ask you to get the configuration for silver? Because now you have to play, the only game you can play to my knowledge is a by analogy game. So you say, by analogy, I see silver is in the same chemical family as copper. So you'd expect silver in the ground state to be 4d10 5s1 or 4d9 5s2. What do you expect? 4d10 5s1, and you are right. Now how about an atom of aurum? Or do you prefer gold? Au. How the hell do you get gold, G-O-L-D, out of Au? Comes from aurum. Latin word for gold. Okay? 5d10 6s1 or 5d9 6s2? 5d10, you're right again. All right, let's go back to chromium and make a prediction about the ground state configuration for molybdendum. Actually, it's molybdenum, but I like molybdendum. A famous female chemist, molybdendum. Molybdenum. Do you expect 45 5s1 or 44 5s2? 45 5s1, you're right again. Now let's go to Wolfram. You're familiar with Wolfram, aren't you? How the hell do you get tungsten out of W? Wolfram. Tungsten. D5S1 or D10, D5S1 or D4S2? What do you bet? D5S1? This time you're wrong. But you were right most of the time. The deal is, when you get to these transition metals, you get some screwy configurations. They're not predictable. So the best you can do is by analogy. And if your analogy is wrong, you've done the best you can with the information you have available. Niobium, for example, same family as vanadium. There is no rule that I know that could be used to come about predicting the valence configuration for niobium. It doesn't obey this half-filled sublevel stuff or half-filled or completely filled sublevel business, nor does it follow Aufbau. We go to the nickel family. Nickel by itself is Aufbau, 3D84S2. But palladium and platinum do not have the same configurations as nickel, nor do they have the same configurations as each other. How about that? So if nickel is 3D84S2 and palladium and platinum have got to have the same number of valence electrons, right? 10 of them, right? And they have configurations which are not the same as each other, nor are they the same as nickel. Now you can predict what the configurations of these atoms are. You won't know which one has which. But one has got to be D10S0, and the other one's got to be D9S1. Because those are the only other possibilities different from D8S2. Isn't it fun? And if you go about the business of measuring paramagnetic character for palladium, you'll find out it's diamagnetic. So it's D10S0. As opposed to ground state platinum, which is D9S1. How many half-filled orbitals? D9S1. How many half-filled orbitals?
2.
How many?
2.
2. Okay? Enough on that stuff. Okay. Now then, one more question on this. Chromium copper. Notice that. For chromium, this correct versus this which is not correct. What measurement would you make if you were in the laboratory where you could make these measurements? What measurement would you make to verify that ground state chromium is this and not this? Paramagnetic character. How many half-filled orbitals? How many half-filled orbitals? 6. How many half-filled orbitals? 4. So this is more paramagnetic than this, and the measurements verify this. Now comes a problem of sorts with copper, because 3D10-4S1 is correct as opposed to 3D9-4S2. What's the problem? How many half-filled orbitals? How many half-filled orbitals? Problem? And now you would have to be introduced to fine, detailed measurement of paramagnetic character, because it is true that a half-filled s orbital, an electron in an s orbital, half-filled s orbital, does not show exactly the same paramagnetic character as an electron in a half-filled f orbital or d orbital or p orbital. A little bit different.
One can also emit different light. There's different.
What is that?
One, the valence electrons release different light, but they would be excited state to the ground state.
Well, I'm sure they would. I mean, you want to do this by X-ray spectroscopy? That's what you're talking about. Yeah, you could do that. I think the paramagnetic character measurement is easier. There are laboratories here on the 4th floor. You can see Mr. Mosen if you got a GUI balance, or what are you using up there?
We use a squid.
Okay, they got a device up there. He probably show it to you if you want to see it, which will allow you to measure paramagnetic character for a sample of matter, like copper or chromium. Okay, now then, let's start getting into laying the foundation for getting at the chapter 23 stuff. Atomic radius versus covalent radius. We already talked about why the covalent radius is expectedly shorter. Illustration. Nitrogen atom. When a nitrogen atom binds with another nitrogen atom to make the nitrogen molecule, you see a big size shrinkage. Because these valence electrons in this thing, the bonding valence electrons in this thing are damn stable. This is the strongest, the third strongest covalent bond interaction known in the world of chemistry. The third strongest. Second strongest is for carbon monoxide. A triple bond in carbon monoxide. And the number one strongest bond in the world of chemistry is for this unusual cation, NO+. Why would you expect this triple bond to be stronger than this triple bond? They're both triple bonds. What is that?
Oxygen is more electronegative.
Oxygen is more electronegative than nitrogen, which means because of the greater electronegativity of oxygen versus that of nitrogen, this triple bond electron density is stabilized even more than this triple bond electron density. How about that? You see what you can do with this electronegativity stuff and paying attention to these considerations that we've offered you? So, much smaller than nitrogen molecule. Now what about covalent radius, atomic radius? Well, for the nitrogen atom, there's the atomic radius. For the nitrogen molecule, here's the covalent radius. You measure the internuclear separation and divide that distance by 2. Now notice that the atom in the bound state has got more than one size. It also has this radius. And this radius is a good deal longer than this radius. This is the van der Waals radius. And the van der Waals radius that's immediately opposite the position of the bond, or in line with the position of the bond, but on the opposite side of the position of the bond, that's going to be the longest van der Waals radius. This size thing is a problem. Now I'll take a quick peek at the hydrazine molecule. How will the size of a nitrogen atom in the hydrazine molecule compare to the size of a nitrogen atom in the nitrogen molecule? Well, it's going to be larger. There's only a single bond. Now then, if I want to approximate the covalent radius for nitrogen and hydrazine, I can take this internuclear separation, divide by 2. But what if I want to approximate the size of nitrogen for a molecule like this? Because when these atoms bond, their valence electron clouds overlap. And I can't tell where the electron cloud of hydrogen stops and the electron cloud of nitrogen begins. Size determination, a can of worms. Pick it up at this point next time.